In this lecture, we're going to consider the results of stress concentrators as they apply to fatigue. The key concept in this topic is notch sensitivity. And the idea is that some materials turned out to be more sensitive to stress concentrators than other materials. So for instance, ductile material is less sensitive to notches, while brittle material in general is more sensitive. And then this is very non-intuitive, but sharp radii actually are less sensitive when we deal with fatigue. Now, when we looked at static loading, sharp radii were very sensitive, and the sharper it was, the worse the concentration was. But as we get into the fatigue study, it turns out it has the opposite effect. So let's define a notch sensitivity as Q, and we're going to let Q be equal to this new concentration minus 1 divided by the old concentration. This is KT, this is the theoretical concentration or the static stress concentration. So this came from, as we discussed before, if you have a static loading problem, you can look up in tables and see, depending on what your notch looks like or what your fillet looks like, you can get some sort of value. This is a function of D, capital D and lowercase d, and the radius of the notch. And Q is scaled so that it's going to be between 0 and 1. Solving this equation for my new concentration, I'm going to get Kf is equal to 1 plus the notch sensitivity times my theoretical concentration minus 1. And now I'm going to say that my stress is actually equal to this new concentration. Now there's a couple things that are interesting here. The first interesting thing is that when Q is equal to 1, we are going to have KT minus 1, we'll just have KT, so the fatigue will be identical to the theoretical. So that's the case where Q is equal to 1. Where Q is equal to 0, we're going to have no effect of the concentration. I know of no material that has a Q equal to 0, but very often we can make the assumption that Q is equal to 1, and therefore the fatigue stress concentrator due to the geometry is equal to the static stress concentrator. If I need to use a table, I'm given a notch radius, and for certain material, this is a graph that's a table that's specifically for steels, and we can see it given ultimate strengths. There's all of these curves that have been curve fit, and I can read off what Q is directly off of this chart. The other way this is done is using Nuber's constant. Nuber is the first one to document this notch sensitivity effect, and he came up with this equation where he has this value of square root of A. And so here's a table of square root of A's both for annealed aluminum and for steel, and this has the same effect. Notice the square root of A that I read off here is directly in the numerator, and the radius of my notch I need to take the square root of my radius so this equation will work. So how does this apply to fluctuating stresses? Specifically when we fluctuate the stress enough that yielding begins to occur. So let's consider the fluctuating stress case where the mean stress is not equal to 0 and the alternating stress is not equal to 0. And again, we have a maximum change in stress from sigma min to sigma max. In the first scenario, let's consider that no yielding occurs whatsoever. So as time goes on, I'm going to be straining up to some point. I reach my sigma max, and then I'm going to be releasing that stress back down to 0. If that's the case, we're going to say that the mean stress concentrator is equal to the alternating stress concentrator. The two of them have the same value. The next case comes about from when failure begins to happen, specifically when yielding begins to happen. So take a look at this figure. Suppose that yielding begins to happen right here at the hole. As this yields, the geometry becomes more stable. So maybe I work harden this part, maybe I change the geometry, it gets thicker. However it is, very likely I won't yield the entire cross-sectional area. I'll only yield locally, and I'll actually strengthen the material in that location. That would look like this. The very first time we load it, yielding occurs, plastic yielding. But from then on, as I load and unload, there's no more change in effect. To take that into account, we're going to reduce the value of Kf. So notice Kfm. So notice at the beginning, Kfm is equal to Kf. But if the stress is high enough that I get into this regime, I'm going to begin reducing the effect of Kfm all the way to the point where I say that the mean has no effect whatsoever on the notch sensitivity. Well, why would that be the case? Consider this third case. In this case, we're doing so much alternating. The alternating stress is dominating so much that we're plastically yielding and then plastically yielding again every cycle. If this is the case, it's the alternating stress that's really doing the dominating work, and the mean stress begins to play basically no part whatsoever, and all we're going to consider is what's happening with the alternating stress. So those are three different conditions, and what this means is that my modified Goodman equation needs to be slightly modified again to take into account the stress considerations, the concentrators. The concentrator for the alternating will always be this Kf that we just talked about deriving, but the concentrator for the mean might not be equal to the same thing. As a matter of fact, this can even be 0 at times. If this is 0, this term goes away, and it's the yield stress that dominates the modified Goodman equation. That's how we handle concentrated stresses and the effects of stress concentrators in the geometry of our parts.